Hello and welcome to a brief video on how to perform the partial fraction decomposition when you have distinct linear factors. Now, from our previous video, we saw some theorems and we saw a process to help us with determining partial fractions. And our first step in this process was to check the degrees of the numerator and denominator. So when we have our example, let's say we have our example, x over 2x squared plus 6x plus 4, the degree of the numerator was 1, the highest power on the x variable here. The degree of the denominator, the degree of my denominator was 2, and that's the situation that you want to have. The degree of the denominator should be strictly bigger than the degree of the numerator. So our second step now is to begin the decomposition. So we're going to say, go ahead and do the decomposition. So what we need to do is we need to factor the denominator, because remember, we're trying to figure out what we were multiplying those denominators from our individual pieces in order to get this denominator we have here. So we're going to take this 2x squared plus 6x plus 4, and we are going to write this as 2 times x squared plus 3x plus 2, and then we're going to be able to write that quadratic as x plus 1 divided or times x plus 2. So there's my factorization for the denominator. Now, what this does is it enables us to get a template for how to break apart this fraction. We're going to break this fraction apart using these guys down here as the denominators. That's what we are attempting to do here. Okay? So we're going to go to a new page. So our third step, now that I know how it's supposed to be broken up, so we have x over 2 times the quantity x plus 2 times x plus 1. We're going to set up a template at some value a over x plus 2 plus b over x plus 1. Those are the factors in my denominator. Now, you might be asking, what happened to this 2? We're going to get to that in just a second, okay? So what we're going to do here is we are going to set up a system of equations. Now, there are many, many techniques for handling distinct linear factors, okay? There's many techniques for handling this, but we are going to set up a system of equations. And the reason why we're going to do a system is because the system really does kind of flush out all of the idiosyncrasies that come up with all of those other techniques you have, like the cover-up method, the substitution method, and things of this nature. The system of equations carries over to all forms of partial fraction decomposition that we will see in this series of videos I'm generating. So we're going to stick with the same technique for each of these because we're not focusing on doing shortcuts or anything. We're focusing on the decomposition process. So this lays the foundation for all of them, and it essentially will go through and say, we're going to do these things every single time. So let's go ahead and set up our system of equations here. So what happens is we're going to take a over x plus 2 plus b over x plus 1, and we're going to set that equal to 1/2 x over the quantity x plus 2 times x plus 1. Okay, and this is where my extra 2 factor comes into play. All right, so when we go ahead and combine these two, just like we normally would when we're adding fractions, we have a x plus 1 plus b x plus 2, and that's going to be equal to 1/2 x. The denominators are the same. Okay, so if you write this over x plus 2 times x plus 1, this is also written as x plus 2 over or times x plus 1. And what we have here is we have denominators are the same, so numerators have to be the same. And this enables me to say that I have a times the quantity x plus 1 plus b times the quantity x plus 2 is going to be equal to 1/2 x. Now we're ready to handle the system that I'm going to put over here in red. Okay, so here we have ax plus a plus bx plus 2b, after doing the distributive property, is going to be 1/2 x. Now what we're going to do here is we are going to match coefficients. Okay, we know from linear algebra that the polynomials form an independent basis if you match up the coefficients. So if you have an x and an x, you can't get x squared by adding things with x's together. You have to multiply them, which is not a linear operation in this case. So we're going to take the x guys that I'm underlining with 2 lines here, and they're going to make up one equation. A plus b has to be 1/2. These are the x coefficients. And then we have a and 2b. So we have a plus 2b is equal to the constant term over here. Well, the constant term over there is 0. Since it's not being shown, that's going to be the constant term. So right here is my system. This is the system of equations I'm going to solve for a and b. We'll start a new page. We had a plus b equal to 1/2. We had a plus 2b equals 0. Now, however you choose to solve this system of equations, that's up to you. In this case, I'm going to go ahead and do the elimination method. Okay, so I'm going to have a plus b equals 1/2. And I'm going to multiply the second equation plus negative 2b is equal to 0. So basically, I multiplied the second equation by -1 to change the signs. When I add these together, I get 0 minus b is 1/2. So this says that b has to be -1/2. So there's one of my answers. Now, because b is -1/2, a plus -1/2 has to be +1/2. And when I add 1/2 over there on both sides, I have a is equal to 1. So these are my coefficients in my partial fractions. So what this says is that 1/2 x over x plus 2 times x plus 1 is going to be equal to 1 over x plus 2 plus 1/2, -1/2, over x plus 1. Now, if you want to check this, you can. Okay, and you just simply check this by adding these two things together. Okay. And when you do that, you will find that this is my decomposition. Okay. And this is how you can do a partial fraction decomposition when you have two distinct linear factors. This is one example. All right. Our next example, x squared over x squared minus 36. Okay. Here, again, our first step is to check the degree of the numerator. That happens to be 2. The degree of the denominator also happens to be 2. Well, in this situation, you're going to need to do some kind of division because this is an improper fraction. The degrees are the same, okay? And the theorem specifically states that it has to be a proper fraction. So how do we fix this? Well, there's a few ways you can do this, all right? A nice shortcut way, because the coefficients of the x squared variables here are both the same, in this case they're both 1, you can do a little itty-bitty trick here by saying, I'm going to go ahead and say x squared minus 36 plus 36 over x squared minus 36. And this becomes x squared minus 36 over x squared minus 36 plus 36 over x squared minus 36. This reduces down to 1 plus 36 over x squared minus 36. And this is now decomposed. Okay, if you wish to do a long division process or even a synthetic division process to simplify this down, you will still get this result here. But now this is in the proper format. Okay, and this is what we're shooting for. And so you want to look out for these little itty bitty tricks. All right, this guy here, this was the add 0 trick. Okay, and it comes from the fact that 0 can be always rewritten as negative a plus a. This is the additive inverse property, okay, from real numbers. So this isn't something that's, always visible. In some cases, it can't always be used fruitfully, but in this particular setup, it can. So this is going to be our new decomposition that we are going to analyze and break down. So now we have x squared minus 36 is equal to 1 plus 36 x squared minus 36. This is the thing that we're looking at, and this is going to be the guy that we are going to decompose. Okay. So let's go to blue. And now we're going to take this 36 x squared minus 36. We're going to factor this as x plus 6 times x minus 6, difference of squares. And now we can write our template out, a over x plus 6 plus b over x minus 6. And we know that a times x plus 6 plus b times x, a times x minus 6 and b times x plus 6, all of that over x plus 6 times x minus 6 has to be equal to 36 over x plus 6. Oops. A little ahead of myself there. X plus 6 times x minus 6. And this is going to give us our system that we're talking about. And we'll go ahead and put this in black. So now we have a times x minus 6 plus b times x plus 6 has to be 36. Remember, denominators are the same, numerators have to be the same when you're working with fractions. So when you have a statement of equality between fractions, the numerators have to match, the denominators have to match, and that's what we're using here. So again, going back to systems, we're going to have ax minus 6a plus bx plus 6b, and that's going to be equal to 36. So again, we're going to combine our like terms, ax and bx. So a plus b is going to be equal to 0. These are the x coefficients. Okay, there's no x over here, so 0 is its coefficient. And then we're going to have minus 6a and plus 6b have to be 36. So minus 6a plus 6b is going to be equal to 36. These are the constants. And this is our system that we're solving. All right. Now, this is primed for elimination method, and that's the technique that we're going to use. A plus b equals 0. Negative 6a plus 6b is 36. We're going to do elimination. So we have 6a plus 6b equals 0. So we just multiplied the first equation by 6. Minus 6a plus 6b is 36. Add them together. Those go away. 12b is 36. B is going to be 36 over 12, which is 3. So we know what B is, and then we can plug that into the first guy because that's a simpler equation. A plus B is 0. A plus 3 has to be 0. So A, of course, is negative 3. And that means my original decomposition, x squared over x squared minus 36, can be rewritten as one whole thing plus negative 3 over x plus 6 plus 3 over x minus 6. And this is the complete decomposition. So one thing you want to be aware of is that if the degrees are the same, or if the degree of the top is larger than the degree of the bottom, you will have to start off with a division process of some kind to get it back into proper form. And then, of course, you're going to factor your denominator. You do not have to factor the numerator. In fact, that makes it harder. So you're going to factor the denominator and use those factors in the denominator of the original fraction to be the denominators of each of the terms in your decompositions fractions. And then you go through and recombine those templates and solve a system of equations. In this case, we had small systems for just A and B because we had fairly simple rational expressions. And this is another example on how you can do the partial fraction decomposition when you have distinct linear factors. So thank you for your time and attention.